Hey, Mickey. Okay, I started typing you an email and I realized it's probably easier just to record a quick video to explain to you what I'm working on over here. I ran into some hiccups with a test I originally wanted to run, which is called the Wilcoxon signed rank test. Now, basically, what it does is it takes your data you've got over here, it takes your coder data, looks at the difference, and then it ranks those differences and it checks to see whether they're positive or negative differences depending on how coder 1 reacts to coder 2. You don't have to worry too much about the ins and outs of the test for a couple of reasons, which you're about to see. So I designed the sheet so if you just grabbed your coder data and pasted it over here, it would update the sheets over here. So you can grab any 2 sets of coder data and drop it in. I was feeling pretty proud of myself. Whoops, I hit the wrong button there. I was feeling pretty proud of myself until I realized something. So you can ignore all this. This is the guts of the test right here. That's the number you have to look at, and don't look at it too closely because here's the problem. When you take that number and then compare it to a standardized number, because this is all about trying to get that thing that we talked about called a p-value. What is the likelihood that the results were gotten due to chance? So what you need to do, and I've been looking at this for about an hour now, this Wilcoxon test, is you need to look up this series of critical values. And why is because your samples are so small. You've only got 7 matched paired data points in each of the studies, which is totally fine, absolutely fine. The only problem is we have to use these tables because we can't use things like the normal distribution and all that wonderful stuff. So I thought to myself, okay, great. So all I've got to do is I've got to use this row right here, which gives us critical values of 7. And then I dug more and more and more into the Wilcoxon, and I realized something. I'm like, actually, no, that's not true. In order to use the Wilcoxon, you have to use the n value, not that's the size of your study, but that's actually the size of the number of data points you have left that mismatch. Now that sounds a little bit weird, but if you look at what I just highlighted here, those numbers are all related to when the coders were different from each other. Those are the ones that get counted. The ties don't get counted, they get thrown out. So for example, this group right here, I would use n equals 5. And I started realizing, I'm like, wait a minute, there's no values for n equals 5. Probably because the sample's so small, you can't really discern any information. So if let's try study 1, if I copy that back in. Now that's only got us n of 3, which is actually off the chart. So I got a little frustrated. I'm like, damn, I haven't run one of these things in so many years, I had actually forgotten about that. But then I started thinking about it more, and I said, okay, that's not the end of the world, because we also had this discussion yesterday about what to call these things, right? You're calling them ratings, 1, 2, 3, 3, and 4, and 4. And then we gave them somewhat arbitrary amounts, 0, 1, 7, 9, and 10, like you said. So I started thinking, I'm like, rather than trying to make something like this that is trying to take a test that already exists and making it fit our data, I said, what if we made our own? So what I did over here, now this is, bear with me here. What I did was, I'm using your ranking system. I got it right here, scale, rating. I took 3 and 4 out and just called it 5. That doesn't matter. That's just a label I put in the spreadsheet to stand for something. So I'm using random numbers over here. I needed to point to a random number, so I'm using that as 5. Here's your scores. And what I said was, okay, let's reverse engineer what we need. We need a graph of some kind that gives us the percent of the time that people match when they're guessing at the coding. So we can compare your sample to it. So what I did here, see if this makes sense. I just labeled these strategies 1, 2, 3, 4, 5, 6, 7. These right here are based on a random assignation. I'm having coder 1 and coder 2 guess at their coding. And you can see that sometimes they guess correctly. Like for example, both of these dudes guessed 3, which means they matched perfectly here. Hopefully that makes sense. if I re-randomize, now they got 2 exact matches. They got strategy 7 an exact match and strategy 2 an exact match. And what I'm doing over here is I'm counting that. I'm counting how many times I see a 0 show up here. I did call it a positive difference. I took the absolute value and just looking at the positive difference because I'm just trying to identify where 0 is. Okay, now if I just keep re-randomizing, I'm keeping track of how many exact matches happen in this chart down here below. Now, clearly, the least number of matches you can get is 0. Maybe they don't match at all. They might not match at all. The most number of matches feasible, possible, is 7. They could match on all 7. Now, it's highly unlikely, and if they're guessing, as I was saying that, a 6 match just popped up. I don't know if you saw that in cell H20. So it's possible, but very, very, very unlikely that you're going to get 5 or 6 or 7 exact matches. It's much more likely that you get 0, 1, or 2 exact matches. So something we can propose to do is to create our own what's called a null distribution. And that null distribution, and actually the percentages are fairly stable right now. The graph is dancing a little bit, but not very much. Those percentages are pretty much sitting at 22%, 38%, 25%, and so forth. So I can just stop it here. We can just chat a little bit. What we can do, and I can let it run overnight if you want to get the distribution to look even better, is we can then take this distribution. I'm going to take a little screenshot of it real quick. And then we can say something like this. Copy. Let's go back to here real quick. And I'm going to delete all this stuff because I can't use, well, maybe I won't delete it yet. I'll just put this on top of it. So what we can do now is we can look at your group here, study 1. There were 4 exact matches. What is the chance of getting 4 or more exact matches, assuming that the 2 coders are guessing randomly? Well, if you look over at this graph, 4 or more exact matches is roughly 3.1% or less, which means that there's almost no chance to get 4 or more exact matches if they were guessing, which is strong evidence that they're not guessing. Does that make sense? Strong evidence that they're not guessing. Looking at study 2. You'll notice in study 2, there were 2 exact matches. What is the chance of getting 2 or more exact matches? You might wonder why I'm doing 2 or more. That's the way p-values work. You look at the chance of your data or more extreme data. So what's the chance of 2 or more? Well, 25% plus 11% is 36%, 39% or so. So assuming that our coders are guessing, there's about a 39% chance. 39% is pretty large. So that means we can't rule out that coder 1 and coder 2 could have had these results due to chance. You see how different that is than study 1? Study 1 is pretty easy to rule out due to chance. Study 2 is not so easy. In other words, they deviated too much. Let's look at study 3. Study 3, boom, 1, 2, 3, 4, 5 zeros. There is almost no way that 5 or more zeros would look like it's due to chance, which means it looks like these are fairly reliable. So what I'm proposing we do here, we can run this through all of your studies as soon as you get them all coded, is we create our own distribution. I call it whatever you want. You can call it the Mickey distribution. We can name it M. But the idea is this is how any statistical test works. It's got a distribution behind it that makes an assumption. For example, in this time, that they're guessing. And then we check your data against that. Now, the first thing I thought of is we are no longer looking at the magnitude. We are simply looking at whether they match or not. That is a problem, right? I mean, you probably noticed that already. I'm only counting the number of exact matches with our model here. I'm not looking at the magnitude. But the more I think about it, the more that magnitude is entirely based on what you choose the values to be. I mean, in your last email you sent, you said, I made them out of a scale of 10. I can make them out of a scale of 100 if you want. Well, I don't know if we can do that, because when you just make them 10 times bigger, any difference is going to be 10 times greater. So I'm actually more tempted to look for exact matches rather than relative matches. Now, I know what you're saying. I know what you're saying, that you also want to look at the nearness of the matches, and we can totally do that. I just, these are just my first thoughts today as I'm thinking about it. It's because as I'm looking down here, I see lots of zeros, ones, nines, twos. There's only certain differences we can actually get, right? We can get zeros, ones, twos. I think we can get sixes. Yeah, there's only certain numbers we can actually get from this data. Only certain differences we can get. So one way we could do it is to look at those certain differences. But then I have to ask you a feasible question. Like, for example, in this particular one here, one coder got a 10 and one coder got a 7. Okay, that doesn't seem too crazy. I think that means one of them said 4 and one of them said 3. But then there's this one down here where one said 1 and one said 3. I mean, are they really going to code them that far off from each other? Like, I think that might be feasibly impossible. Or this 10 and 1 up here, right? This person said 3 and 4, and this person said 1. Is there any way you could actually have a coder have that much disagreement? So think about that. Think about these ideas. Give me some thoughts. We can do a Zoom meeting again. Remember, I got tomorrow office hours run until 3:30 if you want to pop in at 3:30. Hopefully, I'm not going to have time to edit this video. I apologize. I'm going to get it up on YouTube and send it to you. Hopefully you can get something from it. But I'll keep all this stuff open so we can play with it tomorrow if you want to. All right, Mickey, have a good night. Talk soon.